Okay, so we're back at it again. This is TBO problem number 4. I've just seen it now, and yeah, I'm going to be solving this in a style of an interview, so I'll just explain my full thought process. How can you maximize the number of regions n straight lines will divide the plane into? Okay. So let's just imagine I have some kind of plane here. I'm not drawing in the axes because they're probably just going to confuse me. Like, these just look like 2 lines, but if I drew some lines here, this actually is only 4 regions, but the axes make it look like a lot more because they're just there. So yeah, this is just a blank plane, and I'm just going to see what happens when I draw in a few lines. So if n was 1, I suppose the answer is always just 2. It divides a plane into 2 regions. If n is 2, then the answer is 4, unless they happen to unless they are parallel, because then you'd get 3 regions. So if they're not parallel, then it's going to give you 4 regions. Okay. And if n is 3 now, I suppose this is where it gets a bit weird. So if we make this third line intersect along the point of intersection of the other 2 lines, then we get 1, 2, 3, 4, 5. We get 6 regions. But if we actually make this intersect at some other points, now we're going to get 1, 2, 3, 4, 5, 6, 7 regions. So it seems like, let's just write it down, n maximum n, which is just the maximum number of regions these n lines divide. When n is 1, the maximum number of regions is 2. 2 gives you 4, then 3 gives you 7. So it doesn't seem to be... Okay, yeah, okay. So the first part is actually only asking me how. So maybe I can explain this. How can it do that? Well, okay, so let's say we have n as 4. If we add in a 4th line, let's say we did it over here. So let me try and think about this. I want to find a sort of method which lets us generate more lines. So if we have some line here, or let's say a line there, drawing a line which intersects it is going to create 4 regions, I suppose. So if we have 2 lines intersecting, then we intersect a new line along both regions. This is going to generate, well, currently there are 1, 2, 3 regions. And now if we draw a line there, there's 1, 2, 3, 4, 5, 6 regions. And then we get this extra region over here. So I think what's happening is we just double the number of regions with every line we add. So we double the number of regions in the local space where the lines were, if that makes sense. So let's say, I just realized I forgot to put the timer on. I'll put it on for 20 minutes now. So it's originally meant to be 25 minutes, but I'll say I used 5 minutes already. And okay, so let's say we put the line there. So before there were 1, 2, 3 regions. Now if we put the line in here, or here, now there are 1, 2, 3, 4, 5, 6. If we make it intersect with this line as well, we're going to get even more. So I suppose the way we can maximize the number of regions is by ensuring each new line intersects as many lines as possible. So can I make a line which intersects all three of these lines? I guess that would be like that. So yeah, okay. Now let me count the number of regions. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So now there's 10 regions. Okay. Okay. And let's just try one more line and see if we can get anywhere with that. So it appears the way to maximize the number of regions n straight lines will divide the plane into is to make sure each new line intersects all the other lines. Hang on. So if I now draw a line which intersects all of these lines, how can I do that? Maybe something like this. Now it intersects this one, this one. I need to make sure they also don't intersect along a common point. So maybe something like that. Now this one, this one, this one, and this one. So I managed to get the 4 intersections. And now we'll count the regions. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Okay, so that's quite a big jump now. Managed to get 16 regions. Plus 2, plus 3, plus 3, plus 6. I wonder if the 4 lines was meant to be 11. If this was 11, then this becomes plus 4, plus 5. And we seem to have a nice pattern. So I'm going to try and repeat the 4 lines one and see if I can manage to split it into 11 regions rather than just 10. Maybe I missed one last time. So we'll have one line, and I'll make these lines just perpendicular so it's nice and simple. Then 3 lines, so you want this to intersect both like that. Now we have 1, 2, 3, 4, 5, 6, 7. And now drawing in this 4th line, we'll make it do that. So it intersects this line, and this line. Okay, and remember, each new line can actually only intersect another line once, because that's a special thing about lines. We have to write 2 straight lines can only intersect once. That's good to know because there's no way of us making it so that it intersects the same line twice without curving a line. So now this intersects all 3 lines. And let's count the number of regions. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Okay. Yeah, so that means I must have miscounted when I did the previous one. And now there's actually a relatively nice pattern. And I can't actually assume it extrapolates, but, you know, maybe it does. So we'll just assume that for now. And I guess we could predict that for 6 lines the maximum is 22 and so on. So the answer to A, I say, would be for every new line drawn should intersect all previous lines. All previous lines and there should be no shared points of intersection. What I mean by that is if we have two lines intersecting like this and draw the third line, it shouldn't intersect along there, because now we've effectively lost a region we could have had if we just did it there. And this is essentially the same thing as saying no lines should be parallel, since if a line isn't parallel, it's going to intersect the other lines. And there should be no shared points of intersection. Okay, that's what I think the answer to part A is. Now let's look at part B. So we've got this data here, and I suppose we could extrapolate this over. The only problem is I don't know how to prove it yet. So maybe we can look at this case with 4 and see how we can prove it. So, okay, so I'm going to draw a new line separately so it doesn't interfere with all of this stuff over here. Now, if I just make it so it goes... Now that intersects with all 4 of the lines currently. And let's see what happens. So this region is now split into 5A and 5B. Okay. This region, which was originally 4, is now split into 4A and 4B. This region, which was originally 3, is now split into 3A, 3B. This, which was 2, is now 2A, 2B, and 1 is now 1A, 1B. Okay, so I think it's clear that B, whenever a new line is drawn, there are X new regions where X is the number of intersection points. So here there are 4 intersection points, so therefore we've generated 4 new regions. And that's not including the regions which were here before. Essentially, the regions that were here before, we're just splitting them in 2. Is the number of regions, sorry, not regions, intersection points. And following the advice, the answer to part A, if we ensure that each new line has the maximum number of intersection points, so if we're drawing the nth line, like that would imply it has n minus 4 intersection points, which in turn implies n minus 1 new regions. Okay, there we go. So I think this is what we need now. And now we can kind of use this formula to derive this relationship which we see here. Okay, so let's say we have the first line. We now have 2 regions. 2 regions. And that's just from a simple fact that if you draw a line in plane, it's going to separate it into 2 regions. Now, if you draw the second line, that's going to imply there's only 1 intersection point, and I'll call it point of intersection. So therefore, we have 1 new region. Hold on. This isn't working. Because okay, maybe this chain of regions doesn't work, because this would imply we only have 3 regions, even though we have 4. So we have a point of intersection here. Originally there was 1, 2 regions. Now we have 1A and 1B, 2A and 2B. So I guess the number of new regions isn't dependent on the number of intersection points, but rather the number of regions itself, maybe? That's pretty odd. Okay. Okay. Let's just start from the second line. Maybe it's a bit weird for the first 2, or maybe I'm doing something wrong. Let's just have a look. Okay, so let's just say with 2 lines, we have 4 regions. Now with 3 lines, we'll say plus the third line, that implies we have 2. Okay. Okay, hang on. We're running into the same problem, because with 2 lines, if we add a third line, we're actually getting 2 new regions. Sorry, we're getting 3 new regions, because up here we can see we've got 7. So we run into the same issue as that with 1 short, and that's good because it means this formula is likely just wrong, and it's probably actually just n new regions. So now I just need to figure out how to show that. Okay. Okay, so clearly here, we actually got 5 new regions, right? We have 1B, 2B, 3B, 4B, and 5B. So clearly this formula isn't what was before, is completely wrong. And if we draw the nth line, we actually get, well, it would be n new intersection points, but I'm just trying to think how you can justify it. Okay, so if this intersects along 4 lines, that means, let's say we have 4 lines here. Before we have 1, 2, 3, 4, 5 regions. Now if we draw another line, you're going to get doubled the number of regions. So essentially, it's the nth line, that's the number of regions. So that's my justification. Not very rigorous, but we'll leave it as it is. So that means we can use this now to start from the beginning again. And okay, so if we have the first line, well, we just know this gives us 2 regions. I suppose it's because, no, I was going to say with 0 we have, with 0 lines we have 1 region. So with first lines we'd have 1 new region, which is going to give us 2. Then with the second line, we have 2 new regions, giving us 4 in total. Third line, we have 3 new regions, giving us 7 in total. And hopefully you can see the pattern that's starting to form. So for the nth line, we're going to have number of regions is going to be equal to, well, we start with 2, then we add 2 for the second region, for the second line, add 3 for the third line, add 4 for the fourth line, add 5 for the fifth line, and so on till we get to n. Okay, and this is just equal to 1 plus the sum of r from 1 to n. And that's just equal to this formula over here. So this seems to have given us the correct answer. We can test it with some empirical data we have here. So if we put n equals 5 into here, we're going to get 1 plus 1/2 times 5 times 6, which is 1 plus 15, which is 16. So this is my answer to B. There we go. What if we replace lines with circles? Okay, let's see. So if we start off with one circle, that gives us 2 regions. Now with 3 circles, I suppose we're still trying to maximize the number of intersection points. So here, when we draw our second circle in, we need to ensure we maximize the number of intersection points. And I believe because every time there's an intersection point, that's generating some new regions, isn't it? Because if we put an intersection point there, then it just splits this plane into 2 parts. So we need to maximize the number of intersection points. Okay. And not sure if it wants us to give a formula. Let's try. So let's check how much time we have. 2 minutes. We can try and give a formula anyway. So the thing about circles is that now we can actually intersect the same circle twice. So we might do something like that. But that means we just need to ensure we maximize the number of intersection points. So how can I do that? For each circle, we can have 2 intersection points. Okay. Okay, we can think about this as in... I'll come back to this because we've got the next part, although it's just a small part. What does it tell us about Venn diagrams? So clearly, Venn diagrams always maximize the number of intersection points because they never lap over. You never see a Venn diagram which has 2 circles touching. They always maximize the number of intersection points. And therefore, Venn diagrams, by maximizing the number of intersection points, they maximize the number of regions, the number of distinct regions, and therefore show us all the possibilities. How do I say that? And therefore show all possible states of events. Hopefully that makes sense. So if these were events A, B, and C, since these Venn diagrams actually maximize the number of distinct regions, we end up getting all of the different possible combinations of A, B, and C. To display all possible combination of events. Okay, and how can I get this formula? Okay, let's just think about this empirically. So when the number of circles is 1, the maximum number of regions is going to be 2. When n is 2, maximum number of regions is 1, 2, 3, 4. When it's 3, we now have, well, it's still 1 for the entire outside, but now this region has been split into 3b. This is 2b, and this becomes 4b, and this is an extra region of 5. So 1, 2, 3, 4, 5, 6, 7, 8. What the solution is saying now. Okay. So, number 4. Clearly the maximum will be achieved when no 3 lines intersect a single point. Okay, so we got that by saying no shared points of intersection. and no two lines are parallel. Okay, yeah, so we've got that. Nth line adds n region. Okay, so they've stated that, and I haven't actually proved it yet. Well, sort of proved it, but not really. Yeah, well, actually, I suppose I kind of have. If you just imagine these lines were technically in parallel, just for this demonstration. If they're not in parallel, they do something like that. But we can take the region where they've all kind of been separated out, and then if we draw in an extra line, we're essentially just multiplying the number of lines by that. So yeah, it makes sense that the nth line will add n new regions. Okay, if we consider circles, it seems that the number of regions is a power of 2, but this eventually breaks down with 4 circles. Okay, so that's interesting, which means this isn't actually the answer. I think I've actually seen a video on this somewhere. It goes 2, 4, 8, 16, and then 31 or something. So we'll just write breaks at n equals 4. Seems the number of regions breaks down with 4 circles. Right, wait. This is interesting because if you think about it, if you have n events, then there are 2 to the n possible states, right? Because you can either have A or not A, B or not B, C or not C. So you'd believe that since a Venn diagram needs to show every possible combination, there should also be 2 to the n different regions. But it appears this doesn't work after n to the 4, which leads us to conclude that we can't actually build circles. We can't use circles to represent situations with more than four more events, which is why you see Venn spheres, things like that. With one circle, we have 2 regions, and at best, each new circle intersects each previously drawn circle twice. Okay, so with lines, we can only intersect the region once. A circle can intersect another circle at most twice. And therefore, each new circle will add, well, the second circle will add 2 regions, which we see when we have this. It goes from 2 to 4 regions. I guess each intersection point adds a region. Actually, we just went over this, but each sort of intersection point adds, yeah, I'll just say adds a region. Then each new intersection point, well, that's going to intersect with 4 circles, which means it's going to add +2. Then this one's going to add +4. If we can somehow draw one which intersects these each 2 times, then we're going to add +6. So that tells us that the answer to C would actually be, we start off with 2, then 2, then 4, then 6, on and on. And that would imply 2 to the n. Sorry, wouldn't imply 2 to the n. This is a, what do you call this? This is an arithmetic sequence, right? Plus, so this is n equals 2, this is n equals 3, n equals 4, plus, going until the final term, this would be 2n minus 2. Okay, so then with an arithmetic sequence, a equals 2, d equals 2, we can say c equals sum of n, and we'll use the formula n over 2 a plus l, which is equal to n over 2 2 plus 2n minus 2. Oh. Hold on, have I made a mistake somewhere? Oh, it'll be an, isn't it? Sorry about that. N over 2 an, oh no. A plus L, which equals n over 2 plus 2n minus 2. That implies it's just n squared, even though this is clearly wrong. That's weird. I'm making some kind of silly mistake here. Oh, this is an arithmetic sequence. Wait. Oh, we have to add the 2 at the front. Only this bit is an arithmetic sequence. Okay, but then we'd have to use n minus 1. So I suppose an easier way of thinking about it would just be to factor out the 2. Then we get 1 plus 2 plus 3, on and on until we reach n minus 1. Then we can use the simple triangle number formula, where we use n minus 1 instead of n. Okay, and then we just multiply these out. Okay, there we go. That's the easier way of doing it. And that gives us this quadratic formula. Interesting. Okay, yeah. So I'd say I did decently on this question. The first 2 parts I was able to get, but then secondly, we weren't really able to get it. We didn't get the part about circles not being up for the task. But yeah, other than that, I'd say this went all right, considering this was a pretty weird question to think about. Thanks for watching, and I'll see you guys in the next video. Bye.